It's whatever I say it is, because this is my world, yours.
Gee, yes, it has been a bad. All right, let's we have an intruder in what's intruder procedure?
Lock the doors and shock lights.
What if the intruder's in the room?
Adios.
All right. It turns out this would be for the people listening, possibly too. Of course, I'm about to tell you what to do if you can't access the video. So, if you're listening to this, obviously you don't have that problem. So I guess that isn't working very well. But anyway, if you go to our site, I don't know if anybody's tried this, and it seems to be just here at school, so maybe it's not an issue. If you're listening at home and you're able to get on, that's fine. But for some reason right now on our Google site, somehow the videos are not loading and not accessing. But I think it might be just when we're here at school on the school network. So I think they're trying to work on that. But if you run into that, if you just go to YouTube and search Mr. Clark AP Calculus, which is my YouTube site there, and then you can find the date and find it that way, at least temporarily. So if you need to, that's something to think about. So let's talk about section 4.8 here real quick. We have those two theorems, extreme value theorem, intermediate value theorem, okay? And so the extreme value theorem said that if a function's continuous on a closed interval, then there's guaranteed to be a max and a min. For you guys that were gone, the thing we really emphasize there is hypothesis and conclusion. In a theorem, the if statement has to be true for the second part to be guaranteed to work, okay? So we use the example, if your parents said to you, if you get an A, then I'll buy you a car, then for that promise to be good, as we're going to assume, at least right now, that they've been proven, these theorems are true. So if that promise is true, that if you get the A, then they will buy you a car. But if you don't get an A, then the promise doesn't say anything. They could still get you a car, and they could not get you a car. But if the hypothesis is not true, then the theorem doesn't really say anything. Now, the conclusion to the theorem could still be true. You could still get the car if you don't get the A. Okay? So when we say that if a function is continuous on a closed interval, it's guaranteed to have a max and a min. If the function is not continuous or it's not a closed interval, it still could have a max and a min. It's just not guaranteed to. Okay? The intermediate value theorem said if the function is continuous on a closed interval, it will hit all of the points in between the endpoints. It will go through all of those y values. You could have a function that's not continuous or does not have a closed interval, and it could still hit all of the y values in between the endpoints. It just would not be guaranteed to if the hypothesis is not true, if the function's continuous on a closed interval, okay? So it's important to understand those things. So we did talk about a little of this yesterday at the end about the, especially 22 through 25, right? We keep asking about where's the situation it's not continuous. And we gave the example, it's exact one we talked about. On 22, it says there are 37 people in this class 7 days ago, now there are only 12. Okay? Well, the intermediate value theorem would say that you would have to go through all the different numbers between 37 and 12 at some point in time there, and that's not true. You know, because people is not a continuous function, right? Especially because you wouldn't have the numbers in between, right? The half, you wouldn't have half a person or whatever. Okay? But on 23, it says I was 37 miles from home 7 hours ago, and now I'm 12 miles from home. So at some point, you had to be all those different distances in between 37 and 12. Okay? That is a continuous function. Then. All right. Maybe we should talk on 11 through 15 on that section there. There are a couple things I wanted to bring up on that. Oops. Yes, I'm recording, so maybe we should do it here. So if we look at the function 1 over x, So we're looking at a graph that is this, oh, that's really bad. We're looking at a hyperbola that looks like this for 1 over x. Okay, any questions? Some of you asked some this noon already, but anybody have any questions about that section 11 through whatever? Maybe everybody did. Well, Cody, help me out here. What were the ones we were just talking about? Because I know those were 13, 14. Yeah, 12, 13, 14. 13 and 14 kind of hit it from two different aspects. 13 says this. Oops. 13 says if you look at this interval, this function is continuous. So you go, or no, is it closed on 13? 13 is open. Okay, so 13 goes from 0 to 1. And it says this function is continuous on that interval. Now, let's don't forget what it means to be continuous. We learned this back in chapter 2. 3 things have to happen. F of a must be defined. You have to have, the function must be defined everywhere. It must have an output. The limit must exist at all points. Say no breaks and gaps and stuff like that. And then those two have to be equal to each other. The limit and the output have to be the same. So that's what it takes to be continuous. So this function is continuous from 0 to 1. And you can see that, in here, there are no breaks or gaps or jumps. And as you get really close to 0, there will always be an output and so forth. Okay, so this function is continuous. But yet it says there is no maximum. The extreme value theorem guarantees us we have a max and a min. But there is no max because it goes up forever. So why does this not contradict the extreme value theorem? Not a closed interval, right? Again, we can't contradict the extreme value theorem because it is proven to be a true theorem. So why doesn't it contradict it? The fact there's no max? Because it doesn't meet the conditions that it has to meet. The hypothesis. The hypothesis says a continuous function on a closed interval. It is continuous, but it's not in a closed interval. So therefore, it does not have to have a max. Then when you go to 14, they say, okay, well, what about 0, 1? And they ask it a little different. They say, what does the extreme value theorem say? Was it extreme value theorem? Yeah, what does the extreme value theorem say about this function here? So now it is a closed interval. So what does the extreme value theorem say? Nothing. Doesn't say anything. Because? No, not because there's no max. Because the function's not continuous. Right? If you don't get the A, then the promise doesn't say that your parents didn't say anything about what would happen. If you don't get an A, then your parents said nothing about what would happen. They said if you get an A, then they'll buy you a car. If you don't get an A, they didn't say what would happen. If the function's not continuous on a closed interval, then the extreme value theorem doesn't say anything. It is a closed interval, but it's not continuous. Why is it not continuous now? It was here, but it's not here. There's no value at 0. If you include 0, that's fine, but then when you plug it in, you have to get an output. And if you put 0 into 1 over x, you do not get an output, so therefore now the function is not continuous. So again, the conditions aren't met, so the extreme value theorem does not say that there will be a max. Okay? So, there's not? Okay. It didn't say there would be. All right. Everybody read number 17, please. I know we didn't have to do that one, but let's read 17, because that could be a good question. That could be a good quiz question. We're talking about the quiz next week on Wednesday. No calculator. Asking you some questions about these concepts, and there won't be a lot of problem solving and things to do. It's no calculator, but there could be a few things to do where you have to do a few calculations, whatever. So, read 17. Somebody want to tell us how they would attack 17. Show that use the intermediate value theorem, and that's key. Use the intermediate value theorem. So in your answer, you're going, and there will be questions like this on that quiz next week where it says use this theorem. So in using that theorem, you should be stating the parts of the theorem that are important. Okay? Yes, Cody. Sort of. I mean, I guess it'd look kind of like a list of candidates. Yeah, I mean, so from that standpoint, it would look kind of like a list of candidates, but those are the endpoints, right? Those are the endpoints, which is what the intermediate value theorem talks about, right? The intermediate value theorem says it's going to hit all the points in between there if the function is continuous on a closed interval. Now we have the closed interval, so we would have to say that. We'd say, okay, we have a closed interval, 0 to 1. This is a continuous function. Why do we know that? Polynomial functions are always continuous. So since this polynomial function is continuous on the closed interval, and now let's go ahead and plug these in. What do we get if we put in a 0? 2. What do you get if you plug in a 1? -1. And so, since this function is continuous on the closed interval, the intermediate value theorem says it will what? Well, no, it doesn't say it across the x-axis. Well, it doesn't quite say that either. Yes. What I would say is the intermediate value theorem tells us it will take on all values between 2 and -1. That's what the intermediate value theorem says. 0 happens to be a value between 2 and -1, so it will take on 0. So I'd be careful to say, now, would I count that wrong? Probably not, but I wouldn't say the intermediate value theorem says it will be 0, because it doesn't say that. The intermediate value theorem says it will take on all values between the endpoints. So therefore, since this will take on all values between -1 and 2, it will have to take on a value 0, since that is in between. And if it takes on a value 0, that's what a root is, so there would be at least one root. Now, there could be more than one. The theorem doesn't say anything about that, but there's going to be at least one. Okay? So, in a question like that, I am looking to, you could draw a picture of it, plot those 2 points wouldn't be a bad idea, right? And then connect them and say, hey, the intermediate value theorem says it's going to get all those points, that kind of thing. Okay? So that is what you would do on a problem like that. All right. Anything else there? How about the first section, like 7 through 10? We talked about that a little bit yesterday. For those of you who weren't here, it says, does the conclusion hold? And again, that's like in that promise. Do you get the car? Right? You could get the car whether you got the A or not. Right? So you could have a function that has a max or a min and a min without meeting the criteria. You could have a function that hits all the points between the endpoints without having it meet those criteria. So when they say, does the conclusion hold, that's what they're saying. So they're having you look at those functions and say, does the conclusion hold? So on number 7, does it hold? Well, if it hits all the y values between the endpoints, then yes, it holds. Okay? What were the answers? Maybe we should just do that real quick. I don't know if you guys look them up. Why don't we just do that and see if you got that, and then maybe we'll see if you have questions. So on 4.8, number 7, it says yes. Number 8 is yes. Number 9 is yes. Number 10 is no. Okay? So, number 8 says, does the conclusion hold for the intermediate value theorem from -4 to 4 on G? So, might be a good idea to pull this up here. Now, the most common mistake that people make on these intermediate value theorem problems is they forget that it's about f of A and f of B. It's about the endpoints. It's not about the high and the low. So the intermediate value theorem says that this function will take on all values between this point and this point. You get that? So this intermediate value theorem would say, now this clearly is not continuous, right? So the intermediate value theorem really doesn't say anything, right? But the conclusion of the intermediate value theorem is that it's going to take on all points. So they're saying, does it work? So it's kind of like saying, did you get the car? Even though you didn't get the A, did you maybe still get the car? So, do we still get all the points? So between this y value and this y value, 0 and 2, do we hit all those points? So you go up here, are all the y values hit between 0 and 2? Yeah. Yep. I mean, just in this piece alone, it hits them, right? So, yes. Make sense? Okay? We don't have to look from down here. These don't matter, right? It's between the endpoints, f of A and f of B. Okay? All right. So then on, well, any others in? On 10 was the extreme value theorem on this one. So this one is no. So the extreme value theorem, what's the conclusion? That it has a max and a min. Does this have a max? Does it have a min? No, and we talked about it yesterday, because it's open. So -2, you know, no matter how small a number you pick close to -2, I can pick a small one. Right? So there's no min. Okay? Say that again now. This dot?
Yeah.
Oh, good question. What if this dot was down here at -3? Then we'd have a min. Yeah. So then we'd have a max value, we'd have a min value. Another thing that came up in the other class too is, what if you had a constant function? Y equals 7. Does it have a max? What is it? What's a min? 7. That's the same thing, right? Just has a highest point. Yeah, 7. There are no numbers higher on that line than 7. Right? And it has a low point. There are no numbers lower than 7. So that's low point. Okay? So it can be both. So kind of a technicality, but it is true. Because obviously a horizontal line is a continuous function. Right? So it has to have both a max and a min. It does. It just has to be the same.
Number 10, the answer was supposed to be no.
Yes.
Yes, because the conclusion of the ETV says it has to be a continuous function. Obviously, it's not.
No, the conclusion says that it has a max and a min. The hypothesis is that it's continuous on a closed interval. So yes, clearly this is not continuous. So the extreme value theorem does not guarantee that there will be a max and a min, but there still could be. So that's what they're saying. When they say, does the conclusion hold, they're saying, I know there doesn't have to be, but is there? Is there a max and a min? In this case, no, there's not. 'Cause there's no min. Okay? All right, so, you know, so they're not hard questions, but it still, we really want to understand the theorem. We want to understand the technicalities of it and what it's saying and so forth. All right, because these things do help us in some of the important things we do in math, and that's why we don't do a lot of theory, but these are important enough, because we do a lot of work with max and mins, for example, okay, finding max and mins. And the intermediate value theorem, like the Newton's method, the thing with roots and stuff like that, because we're interested in roots, so that's important. And then, of course, the next one we do on Monday is probably the most important one of all. And so we'll talk about why that is important with a lot of the ideas. Okay? All right, well, let's move on. I want to do some work with the packets, maybe answer a few more questions for you, and then give you a decent amount of work time today on your packets, maybe even on your take home. I mean, the intent of it is to kind of take it home. That's the thing. But if you want to work on it today, you could. And that is due on Tuesday. That's true. Good point. All right. So anything that we can do to help you out still on sample 2? Yes.
Number 26.
Number 26. That is a no calculator, I believe, right? Okay. Number 26 says a normal line to the graph of a function is defined to be the line perpendicular to the tangent line. Okay, so now hopefully we know about doing the equation of a tangent line, right? That's this. So, the normal line would just mean, what do we think of, or what do we do with perpendicular? Opposite reciprocal slope. And slope here is derivative. So, wouldn't it make sense to do the derivative, find that slope, plug in a 3, and then do opposite reciprocal, and then put it into our equation. So that is what we want to do. So maybe at that point, the rest maybe is okay. Was it kind of that getting started with it, Shelby? Or okay. So when we do that derivative, and it doesn't hurt to go through this. Usually, hopefully, I mean, it looks kind of messy, but hopefully the numbers work out pretty nice. You know, so a little practice with derivative, obviously. A cube root means 1/3 power. These are kind of things we're trying to review by doing these packets. Little things like derivative rules and those kind of things, but also putting together these ideas that we learned. So now that's your derivative. So we're going to plug in our 3. And then 2 times 3 would be 6. So then the question is, we got to be able to work out 8 to the negative 2/3. How does anybody got a plan for that? Okay. And that's fine, because the order that you do this, when you square and then cube root, doesn't matter. I would rather cube root it first, just to keep the numbers smaller, right? So what's the cube root of 8? 2, and then squared. 4, now it's negative power, so what's that mean? It'll be flipped over, right? It'll be flipped over, so it'll be 1/4. So in other words, this will be 1/3, and so then this is, what do we say, 2 squared 4, 1/4. So this would be 1/4, and then 6. So that that might be one of the harder parts of it. I don't know. But yeah, because the negative power really means 1/8 to the 2/3. So it's 1/4. So that's 1/12 times 6. 6/12 is 1/2. So the slope we want is -2, right? Opposite reciprocal. So now we come back to our tangent line stuff, and so we go y equals -2. Then we put our point in, we get x minus 3. And then how do we get our y point? Go to the original equation. So we put our 3 here, 9 minus 1 is 8, cube root of 8 is 2, and so that's our y point. And then it's a matter of getting it to look like this. So we get y equals -2x plus 6 plus 2, y equals -2x plus 8. Add the 2x over, just because I'm looking at my different answers there. And it looks like D. All right, any other? Any free response ones? Anybody? What about number 3 on the free response? I just say that because the other class asked about that. That'd be it. We do that one. We didn't do number 3, did we? We did 4. 4 and 5. We do 4 and 5 yesterday. You want to look at 3? Okay. Think. All right, think about 3. This, a lot of times they'll do a problem like 3 where they put that B in there. It kind of, this is a calculator one, but the calculator doesn't help you a whole lot for various parts of it. Now, with the CAS calculators, you can do some things with the B in it, probably, so you probably could do some of what we're going to do with your derivatives and some solving and stuff with your CAS calculator. I don't know, I haven't really emphasized that much and shown people and worked it much on the calculator, because quite honestly, I don't think it always works very well, and it kind of depends on the problem, and I think we're better off trying to do it the way that they intend here. I just think it's better conceptually for our understanding of what's going on and so forth, and I think nowadays a problem like this is one of the reasons, see, it used to be all 6 questions you could use graphing calculator, free response on the AP. And then as the CAS calculators came in, even though they didn't outlaw them, it was a small number of people used them. So it wasn't that big a deal, but then they started to realize that some of the problems, the people with the CAS calculators had an advantage. So then they went to 3 questions multiple choice, or 3 questions calculator, 3 questions no calculator. And then they made some of them like this, where the calculator, even though you could use a calculator, didn't really help you much. But yet then the CAS calculators kind of could do this. So even when you could do all 6 of them with a calculator, you know, you couldn't really do anything with this on a regular graphing calculator. Well, so now they've changed a number of years ago, 3 or 4 years ago, to 2 with a calculator and 4 without a calculator. So they're slowly going towards more of a no calculator. So a problem like this might nowadays be on the no calculator, quite honestly. So that's how I'm going to go through it with you. Now, the exception would be right here where they give you a viewing window and it says graph. So here they would expect you to use a graphing calculator. So maybe they would do this, they wouldn't do part A. They'd do something different with part A. I don't think they would make you draw a graph of this without a calculator, I'm sure. Okay, but the rest of it I think they would make. Okay, all right, so you plug a 1, so this part's pretty easy, right? You plug a 1 in for B, and I'll just estimate what this looks like, but it's going to give you a cube that kind of does this, right? And then you plug a 2 in for B, and you're going to get a different one. And it's going to come down. Now it's going to still go through 0, 0, and then it's going to go up like this. And then you plug a 3 in for B, and then it's going to go like this. And it's going to come down, and it's going to do this. Whatever. Right? Those are awful. Anyway, that's what's happening. So you've got this family of functions, these cubic functions that are doing this, looking something like that. Okay? So that's all you have that they wanted you to do a part of. All right. Now, if we go to part B, and B and C kind of go together. It says find the x, y coordinates of the relative max points. Relative max and local max mean the same thing. So what's our strategy to do that? What's our strategy to find local max and local min? Derivative, then what? Set it equal to 0. So we've got this equation right here. So we do the derivative, which would be 3x squared minus 3b, right? B is just a number, so 3b is just a number in front of x. Derivative of that would be 3b. And we're going to set that equal to 0. So we go ahead and we solve that. We get 3x squared. We could factor out a 3 if you wanted to, but basically we could just probably do that simpler. Divide by 3. Do the square root. Don't forget plus or minus. Plus or minus square root of b. So that's where the derivative is 0. Now, we've already graphed the thing, so we know the first one's going to be a local max, right? And we know the second one's going to be a local min. And we've already graphed it, so we know it's got a local max and a local min. It's a cubic, okay? But they want the x and y coordinates of those in terms of b, which means b is going to be in our answer. So when we do the derivative and set it equal to 0, what's our next step in a local max problem? Huh? To what? F prime, right? This is not an absolute max. This is not a global max problem. We're not doing list of candidates, right? What are we doing? Why are we plugging them back in? Negative or positive. We're doing a number line. It's a number line, right? That's what we do with local max min problems. We do a number line. We want to see when F is going up and then down. We want to see when F prime is positive, then negative. We're doing a number line. So we take these numbers and we put them on a number line. Okay? And so we got negative root b and we got positive root b. Right? Some of these things, now, you get frustrated. I got a little frustrated. I got frustrated with the other class. It was funny. Because I was, on the one hand, I was getting frustrated. They weren't remembering these things. And then I said, but that's why we're doing this review, right? So I can help you to remember these things. So it shouldn't surprise me that you forget some of these things. That's why we're doing this review, right? That's why we're preparing for this midterm. And so it's just that sometimes I think, like, God, I must have done a lousy job of teaching this. If we're not remembering this stuff. So anyway, so if I sound like I'm frustrated with you, not really. It's not you, it's me. All right. Anyway, so those are those stationary points we put on. Now, what makes it tougher is you got the b in there. That does make it tougher. It's nice when they're numbers, all right? So we got some things we need to do. Now, what do we do on our number line? What do we do in between here? Pick numbers that are in between, right? So an easy one would be in between here. 0. Now, I think it did say b is positive, right? We do know b is positive. I think, right? They said that. Okay. Yeah, so b is greater than 0. So we know b is positive. Yeah, it has to be, right? It has to be. X squared is positive, so certainly b is positive. All right, what is a number bigger than square root of b? 2 square root of b. Or b. Or square root of b plus 1. Now let's talk about those. Remember, whatever one of those I pick, what am I going to do with it? Into f prime, right here, right? So when I plug it in, I'm going to have to square it. So when I think of square root of b plus 1 and squaring that doesn't sound like a lot of fun. So rarely is that a choice we make when we're doing one of these problems with numbers or with letters, is a plus 1 thing to make it bigger. Because then it usually is more difficult to work with later. Okay, so that's the first thing. What about b? Is b really bigger than square root of b? You sure? It depends what b is. Numbers between 0 and 1, this is not true. Let's say b is a fourth. What's square root of a fourth? 1/2. Is 1/4 bigger than 1/2? No. So b is not necessarily bigger than square root of b. When you do a square root of a number between 0 and 1, it actually makes the number bigger. Okay? So that's another thing we got to be careful of. So just by squaring something does not necessarily make it bigger. Okay? If it's a number between 0 and 1. So we have to be careful of that. So the best choice was the other one that I heard, and that's typically the best choice. If you multiply by 2, positive number, it's going to make that bigger. Okay? And that is a positive number, square root of b, and so that's going to make that bigger. All right, what would be a number littler than negative root b? Negative 2 root b. If you take a negative number and multiply it by 2, you make it littler, right? And so those would be ones to choose, and those are going to be easy to square and plug in. And so now we do that. So that's the hardest things in that problem is realizing that. Now, next time you run into a problem like this and you have B's and A's and things like that on your number line, it'll be easier for you to come up with those values. All right, so we want to plug those in. So 0 first, that's an easy one. 0 minus 3b. Positive or negative? Remember we said b is positive, so that is going to be negative, right? So let's go 2 squared. Now, to be honest, when you have to plug these values in, you just graphed f a minute ago. What did it do? It went up, it went down, it went up. Then we know there's going to be positive, negative, positive. We do. We know it's going to be. So you could probably put that on. But because on showing the work, you don't have to show your work on where that positive may come from. Remember, a number line, when the AP graders grade a problem with a number line, they do not grade the number line. They grade your written response to the number line. Remember when we talked about that with local max? We'll get to that in a second. But let's just do it just for the heck of it here. So 2 square root of b, maybe you didn't have one where you didn't know the graph. Maybe you would actually have to plug these in. So let's do it. So if I square 2 square root of b, what is that? 4b, right? 4b times 3, 12b. 12b minus 3b, 9b, which is positive, right? So this comes out positive. And then on this one, when it's a negative, we put it in, but we're going to square it, so it's going to come out the same. So it's going to be 9b, so that's going to be positive. So we end up with this, which of course is what we knew the graph did. It went up, down, then up. But here's what we've got to do. We've got to answer the question. Find the x and y coordinates. So the local max is this one. So negative root b is the x value. What's the y value? How do we get it? Plug it into the original. Okay, so that'll be interesting because we got to cube it. Now, if it were me, I would write this, if I'm going to cube that, I would write that as b to the 1/2. That'll be easier to cube. Because when you cube something, power on a power, you do what? You multiply. So when I put in negative b to the 1/2 into here and cube it, that's going to be negative b to the 3/2 minus 3b times negative b to the 1/2. Well, what do I do there? Here I would add the powers, right? So what's 1 1/2? Oh, 3/2. So this is negative b to the 3/2. Negative times negative is plus 3b to the 3/2. What's that? 2b to the 3/2. So there definitely is a little bit of algebra and arithmetic and those kind of things to do right there. That is your local max x and y coordinates in terms of b. Now, you would need more though. To tell that this is a max, we would have to do that explanation. We would have to say that since at negative root b, f prime is changing from positive to negative, f is changing from increasing to decreasing. That's why it's a local max. Don't forget that. When you go to C, you would not have to repeat all this work. You could come down here and you could say, in part B above, we found that, and then we would do the minimum here. Now you plug this in and it's basically the same idea. We found that that point is a local minimum because f prime changes from negative to positive, so f changes from decreasing to increasing, and then the coordinates, and that would be part C. All right, and then part D. Show that for all values of b greater than 0, the relative max and min points, which are the ones we just found, right? We had negative b to the 3/2, 2b to the 3/2, and then we had the other one, which I think was b to, oh no, that was b to the 1/2. And then the other one was b to the 1/2, and then I think then this came out negative 2b to the 3/2, I think is what the other one comes out to be. So the first one's your local max, and the second one's your local min. Show that for all values of b, the max and min points lie on this function. Find the value of a. So what do you think you're going to do? In for x and y, okay? Because that's what it means. If a point lies on a function, that means it's x, that's the x and the y in the function. So if these points are on this curve, then plug them in for the x and the y. Now it turns out you can just plug one of them in, they come out the same. And so for the y, I'm going to put 2b to the 3/2. And over here I'm going to put negative a, and then x is negative b to the 1/2. And that's cubed. And so I get 2b to the 3/2 equals negative a, and let's see, what is this? When I cube a negative, it stays negative, so that's going to make that positive. And then this would be b to the, oh, what's a going to be? A's got to be 2. Right? Pretty easy there. And it turns out to be the same if you would plug this in. A's got to be 2. Now, it's somewhat common in the free response that they do this, where each part leads to something else, and then all of them taken together give you some interesting information about the entire problem. Not always. So the downside is sometimes you get a problem like that, and if you can't get the first part, it makes all the other parts hard. But there are other problems where if you can't do part A and B, you might still be able to do C and D. Okay? Or maybe you can only do part A and C, or whatever. So don't give up on a problem just because you can't do one part. All right? But in this case, it really ties all this together. So what they're saying here, let's think about what they're really saying here. They're saying that on those 3 curves that I drew in the first part, that those max and mins all lie on this curve right here. Negative 2x cubed. It's kind of cool. If I go back, and you can do this on your calculator, if you've already graphed those things and have them on there, it basically means, let's see if I can do this justice. So what they're saying is, if I draw, when I had b be a 1, a 2, and a 3, so when b's a 1, it comes up and does this. And when b's a 2, it comes up and it does this. And when b's a 3, it comes up and it does this. And here's my max points here. Here's my min points here. And what it's saying is, so if you had that graphed on your calculator, and then you went in and graphed this graph right here, guess where it's going to go? Like that. And no matter what you let B equal, and you can graph a whole bunch of them, let B be something different every time, in that family of curves, the max and mins will always be on this red curve, which is kind of cool. Okay? Is it useful? Well, that's kind of cool. Probably useful in some settings, but all right. So that, I mean, but that's what that altogether, taken all together, that's kind of what that problem got you. All right. I'll tell you what, at this point, we got 40-some minutes left, so maybe this would be a good time to just let you work. We've got, again, the Tuesday, the take-home is due. If you want to work on some of that a little bit, you can. I told the other class I would post online, but then somebody came up and asked about it and drew it on the board, and I said, oh, I guess I don't need to post it. There it is. So here's what we did in the other class. I'll just show you guys as well. Number 4 talks about carrying a pipe. I don't know if you may not even read it yet. Everybody got the sheet? Okay. Carrying a pipe down the hallway, and you're going to make a turn. That one, and now we're carrying it horizontally. We can't tilt it because that would make the problem just more complicated, right? I mean, because then we'd add another dimension, and then that would get confusing. That's what you need Calc 3 for. Calc 3 gets into X, Y, Z, and 3-dimensional. It's interesting. But double derivatives and not second derivatives, but anyway. So basically the idea is this. So you've got a hallway, and then that turns into another hallway. The first hallway is 4 feet wide, and then the second hallway is 8. So clearly that hallway is twice as wide. All right. So turning or from an 8 into a 4, whatever, doesn't really matter. It does. Okay. But so the idea is we're going to carry this pipe horizontally. So we're coming up here with the pipe, okay, and then we're going to make the turn, and then we're going to go, what's the largest pipe we can have that will make that turn? So then the question that this person was asking is, okay, is this what my drawing would look like when I draw the pipe? Anybody have any thoughts or anything about drawing the pipe, making the turn around the corner? Triangles will be involved, yes. And they'll make a triangle, and where would I draw the pipe? So like here? Oh, but then a bigger pipe would be there. And actually bigger. It's going to have to just scrape the corner, isn't it? Right? Yeah, that's kind of the first important element of this problem is that your picture for the pipe, and what are the chances I can draw any kind of a decent looking pipe? I know what I can do. I can cheat. Oh. There. All right, so that would be the picture, right? So the pipe would have to just touch, and of course, then usually, people think, well, how thick is the pipe? Well, we have to ignore that too, right? To make it so the thickness of the pipe, and maybe that wouldn't matter. Let's see if we touch on that again. Yeah, it's kind of weird. So that's the idea. Is as it makes that turn to maximize it. It's going to have to just touch there and just touch there and just touch there. Because if it's smaller than that, clearly it can make the corner. So we want the largest one that can make that corner. So the largest one is going to be the one that just barely fits going through there. So now I've seen people set this up at least 3 different ways. Because there's triangles and angles and so forth, and there's gonna be similar triangles and all kinds of different ways that you could set that up to end up getting. But it's just, other than that, it's just a basic maximization problem, right? You wanna find the largest pipe, so you need to set up a pipe length equation, you know, in terms of one variable. So that's my hint, that's my help on that. Okay, so at least you can get you started there. All right, so the rest of the time you can work on the new packet, because I think you really need to get going in the new packet, to be honest with you, exam 2. So it depends where you want to spend your time. You know, how, if you want to use it, some work time together and take home, I'm fine with that today, but that'll be about all the in-class time we have. And Monday will be other stuff. And I think you want to get a decent start on that packet too, because towards, you know, Tuesday or so, we'll probably get the last packet. So we want to be going in the packet. Okay, so some of both, go ahead, and the rest of the time's yours to work, and I'd be glad to help you if you got questions. Yes.